So this session today is the deep dive into the kernel of the .NET framework, which is also known as the CLR. Before I get started, I thought I'd introduce myself and my colleague Mark here. I'm Prachiti Nagarkar. I'm a program manager on the CLR team. Actually, it's called the .NET Core Platform team. I am a program manager, so what I do is I try and understand customer scenarios, figure out what features we need to build to satisfy those scenarios, work with a team of devs and testers, and get the product built. And then I get to talk to a team like you guys to explain what we built and hopefully get feedback about whether it's working or not. And on the CLR team, I own a bunch of different things. I own how .NET assembly loading and binding works. I also own how we handle resources and localized assemblies that contain localized content. And in the past, I've also worked on native image generation, or NGen. So if you have any questions about any of those, I'd love to hear from you at the end of the talk today. And you can stop by. And this is Mark here.
Yeah. So some of you may be a little bit, some of you may be a little bit confused seeing my face up here. Maybe you were expecting maybe someone with a bit less hair. I'm not the Mark Miller who works on DevExpress. I'm the Mark Miller who works on the .NET Core Platform team. And the little cryptic letters there next to my name, SDET, that just means that I'm a tester on the CLR team. That means I get to have a lot of fun breaking the things that we make so that you guys don't have to. I've owned some of the same technologies that Prachiti talked about: native image generation, assembly loading, type loading, things like that, as well as in the past I've owned runtime activation, MS Core EE, the shim. Improc side-by-side and those kinds of things that in the past. So again, if you have any questions on those, in addition to the things that we're talking about today, we can answer those questions in the expo hall after the talk.
OK, thank you. I'm actually really happy you're the right Mark. I'm sure the other Mark Miller is a great guy, but I'm kind of happy you're here giving the talk with me. So this is day 4 of this conference, and you've been seeing a lot of stuff that Microsoft's been working on. Clearly, we've been hard at work building the latest set of advancements to the Windows 8 platform. But we're also working really hard to make sure that .NET developers have an excellent experience targeting that platform. And so we've done a whole bunch of work over the last year or so, and we want to make sure we can talk to you about that. And if you are writing any kind of .NET-based app today, like if you write C# code, that may be if you're going to write C# code to create your Metro-style app. Say you're using WinRT APIs, and you're also writing, you're writing that in C#. You are running on top of .NET. So I know this has been a point of confusion for a lot of people out there. I'm just curious how many folks attended Joshua Goodman's talk earlier this week about advancements to .NET Framework 4.5. Okay, that's a lot of you. I know Christoph had a talk just before this about WinRT and .NET APIs. How many of you were lucky enough to get into that? Okay, good to see. So hopefully, some of the confusion around, where's .NET, where's the CLR is hopefully starting to clear up. So if you are writing any kind of .NET code, any kind of C#, VB, or any other CLI language, you're running on top of the core execution engine of the .NET framework, which we call as the CLR. And I'm going to throw up a picture here really quick. This should seem familiar from Joshua Goodman's deck earlier this week, and it is the same exact slide. I thought I'd throw it up here because I just wanted to explain where the CLR sits in the whole .NET framework. And you can see that some of the more things that may be more familiar to you are the ASP.NET stack, there's WCF, WPF, and of course there's Workflow Foundation. And those are all layers and frameworks that are built on top of the core execution engine of the .NET framework, which is called the CLR, or the Common Language Runtime. And some of the things that the CLR does for you, which you may or may not have noticed, is we handle how assemblies get loaded. We try and figure out where they live. We load them in. We take the IL content that lives within the assembly and compile that into native code via JIT or NGen. Of course, we have a security model to make sure that your apps are running safely in a secure environment. And we have a world-class garbage collector that we use to manage memory. So the garbage collector will allocate memory for managed objects and reclaim memory for objects that aren't getting used. We do have a exception handling model. All code needs to report errors and throw exceptions. And so our stack can handle the exception unwinds and all that bookkeeping that's needed. And of course, we also have a profiler. We provide profiling APIs on top of which other people can write profilers, actually. And we have a good set of debugging APIs. And the last part is the one that you're probably the most familiar with, which is we provide a set of core base class libraries that all of you can write C# or VB code in your apps and libraries against. So I'm just curious at this point, how many folks in the audience are C# or VB developers? Wow, I love this. This is so great. So this talk is for you. This talk is clearly aimed at .NET developers. If you have written C#, VB, managed C++, this talk is going to go deep into how into some of the improvements that we made in the 4.5 version of the CLR. And if there was any kind of theme for today's talk, it's performance, performance, performance. And I'm going to talk about, we're going to spend a lot of time today looking at some of the performance improvements that we've made to help some of your .NET apps just run faster, use less memory, and have faster startup time. And so we'll spend a lot of time looking at that. And we'll also spend towards the end spend time looking at a pretty cool diagnostics feature that we built in 4.5. What we hope you leave with today is a really great understanding of what's new in the 4.5 CLR. We're innovating a lot in this space. We're not actually going to have time to cover everything that we've done in the 4.5 CLR, but we'll try and cover the big ticket items today. And hopefully you can also leave with a very good understanding of how to leverage some of these improvements that we made. So with that, let's get started with the garbage collector. So how many of you guys, just to gauge how much the audience knows about the GC, how many of you think you know what a Gen 2 collection is? Fantastic. This is great. I should tell my GC team back home. So there were some hands that went up. That's great to see. There were some hands that were still down. And because of that, I think the GC is a fairly complex component of the CLR. And so I think before I actually talk about the improvements that we made to the GC, I want to spend some time making sure that the fundamentals about the GC are clear to everyone and we're on the same page. And since this is a CLR internal stock, my job here is really to teach you about some of the fundamentals here. And so hopefully when you leave, you kind of have a better sense for what the GC is and what some of the other areas are. So there's two concepts I want you to take back with you from this slide. The first is when the CLR starts up, we allocate two heap segments. We allocate a small object heap where small objects will live, small managed objects will be placed. And we allocate a large object heap. And this is for objects that are greater than 85 kilobytes in size. And on server mode, we do have another mode in which our GC runs. On server mode, we multiply that by the number of logical processors that exist on that machine. So server GC is scalable. It scales better when you have multiple cores. The second concept to take away is that the CLR's GC is a generational GC. And you've probably heard that somewhere. And some of you may be wondering what that means. And the way to think about that is that when managed objects are allocated on a heap, they get placed into logical buckets called generations, depending on their lifetime. And so if you have a new object, it will always get placed on the first generation, which is generation 0. We're all programmers. We love 0, right? It starts, that's the first number. And so all new objects will get placed on Gen 0. And the other reason why it's called a generational GC is that when we collect memory that's no longer being used by managed objects that are no longer alive, we do that on a per generation basis. We don't go ahead and clean up the entire heap because that could take forever. And the GC wants to be as efficient as possible. And so the generation 0 collection will only collect free memory from the Gen 0 portion of the heap. The Gen 1 collection will collect free memory from the Gen 1 and the Gen 0 portion of the heap. There's a little nuance there. And the Gen 2 collection collects memory from across the heap. Okay? And so that's how collections work in general. And so in this diagram, actually, what you can see, I'll just go back here really quick. What you can see is there's only a single heap. I only have a single heap up here for simplicity. I did say there were two heaps. The red squares up there represent your managed objects, which in the GC world we call roots. And only if you have a managed object that's still alive will we keep the memory for it alive as well. And so, of course, we can do, and occasionally when the GC does collect this free memory, the other thing to remember is it can compact the free space so that you're using a contiguous memory segment. So the next time you want to allocate memory, you have a nice, clean, open space to work with. And the last thing to remember is that when free memory is collected from a generation, if there are any objects that survive that generation, that garbage collection, they will get moved to the next generation. So any objects that survive a Gen 0 collection get moved to Gen 1, and anything that survives a Gen 1 collection gets moved to Gen 2. Okay, so there's like a little chain, and Gen 2 is the last one. We don't have anything more after that. So I did mention that there's our GC runs in 2 modes. If you have a .NET app today that you haven't done anything special with it, then you are running in the client or workstation mode. And there is another mode that our GC runs in, which is the server mode. And really that should be called, I think Joshua mentioned this in his talk, it should really have been called the multi-core mode, because it scales well when you have multiple logical processors. And I did say, there's multiple heaps. There's 2 heaps created. There's heaps created based, the heaps that are created are multiplied by the number of logical processors on your server. And in terms of collections, so actually the one thing I want to talk about regarding collections is, so I talked a little bit about, hey, there's these Gen 0 collections, or these Gen 1 collections, or Gen 2 collections. And there's an interesting mechanism by which they run. And this is sort of important to get right for the purpose of this talk, actually. So the Gen 0 or Gen 1 collections, they happen to run on a smaller portion of the heap, right? So Gen 0 and Gen 1 tends to be a smaller sized memory segment. And typically, the GC can go in and quickly collect whatever it needs to collect from those 2 heaps, and those 2 segments of the heap. And so because of that, because it's so fast, when the CLR GC actually does a Gen 0 or Gen 1 collection, we will actually go and pause any managed threads that are running in your app. We'll suspend them. We'll go run our GC work that we need to. We'd go finish that off quickly, and then we resume your managed threads. So the Gen 0 and Gen 1 GCs will block the execution of your managed app. And the idea is that we think that there should be a very, very tiny fraction of time. You shouldn't notice it at all. And so that's why we do that. The Gen 2 collections, however, remember they operate on the entire heap, right? And so they can take a long time to finish. And clearly, we don't want to be pausing your app when we do that. That would just be awful. Thank God we don't do that. And so the way the Gen 2 GCs collections are handled is we basically we create a background thread, and we run the collection on that background thread. So we don't pause your app can happily continue running, and we're doing this collection in the background. And in general, this is a great thing, right? So I want to just make sure that this mechanism of suspending and resuming sort of reaches you guys. And so I have a quick diagram here that shows server GC. You'll see there's 3 threads that are running. They're allocating away. There are 2 GC threads because the app that this example is from was running on a machine that had 2 logical processors. Okay, so we created 2 threads there. And these 2 threads happen to be handling the Gen 0 and Gen 1 collection. There will also be 2 threads to handle the Gen 2 collections. In this particular example, I don't show that. The arrows in red tell you that the GC is actually happening. And you'll notice that at the same time, those arrows in blue represent that your managed app is suspended, right? So that should be fairly clear now. So in general, this is great, right? We do our Gen 0 GCs quickly, Gen 1 GCs quickly. Gen 2 is given a dedicated thread to run on. And this should be great, except in some scenarios where sometimes when a Gen 2 collection is in progress, occasionally your app, of course, is continuing to execute, right? And so it may actually want to create small-sized objects really quickly. Like say you want to create a small object, custom object that you created in your app, and you just want to quickly create that. But in case the Gen 0 or Gen 1 heaps ran out of memory at that point, and you actually need to collect them to gather free space, then now what the GC also does is it will actually as of .NET 4.0, it will wait until the Gen 2 collection that is in progress finishes. And so now .NET apps are getting larger. You know, they're creating, there's lots of heap sizes are getting larger in general. Say, you know, your app is managing a large cache. And so with all these heap sizes getting larger, like that Gen 2 collection could take a while to finish. And we don't want to pause your app while the Gen 2 collection finishes. That's the last thing we want to do. And so this big improvement that we've introduced in 4.5 addresses that exact problem. So I'm going to throw up a diagram here that sort of is a schematic for how some of this synchronization happens. This is an internal stock, so you get to see all the gory details, right? So over here, again, we have the same app. You know, there's 3 threads. They're allocating away, running away. There's 2 GC threads that are going to be handling your Gen 0 and Gen 1 collections. And there's 2 background GC threads that are going to do your Gen 2 collections, which is, you know, same as always. But the interesting thing to note here is these 2 little green arrows. So notice that those 2 green arrows are happening on the threads that handle the Gen 0 and Gen 1 collection. So as always, they will end up pausing the managed threads. And so that's the top 3 blue lines over there. They will end up pausing your managed app. But the critical thing to notice here is that those GC threads got a chance to do their Gen 0, Gen 1 collection while that Gen 2 collection was going on. And this is the big improvement that we made in 4.5. So because of this, you can your app can continue running. It can make these small allocations that it needs to, and you reduce the pause time that you would have encountered previously, and the Gen 2 GC can continue afterwards, right? So it lets these small allocations continue. You get reduced pause times, and the app is a lot happier. It's a much better experience there. So that's the big thing. For those GC fans in the audience, you may have picked up on the fact that, hey, this looks awfully similar to something we did for client GC in 4.0, and it is. It is in 4.0, we actually added this feature for client GC. We didn't get around to adding it for server mode. And so 4.5, we've actually added it to server mode as well. So this improvement has been brought over to server. So client and server should be at parity from this respect. So our GC team is fantastic, and they've been busy building lots of other things for you as well. Some of the other stuff that they've been working on is we now have what we call scalable marking for full blocking GCs. And marking is this phase, you know, it's a fancy word, but essentially what it is before you can actually do a collection and you can reclaim memory, you have to figure out what objects are actually alive or dead. And so you start off with an object, and then you recursively walk the entire object graph to figure out what's dead or alive. And in server GC, like typically, you know, one of the threads will pick up an object and it will start doing all this work, right? But what if this particular thread is trying to do marking for a huge object graph, and now there are other threads that are sitting there idle that could actually help with this work. And so what scalable marking does is it steals some of this marking work from that other thread that has a ton of work to do. And so with that, like hopefully we can reduce the time that we spend doing marking overall, and that should be it should reduce pause times as well. There are other improvements that we've made to how allocation works against a large object heap. We make better use of free space on the LOH. And we're also balancing the size of the large object heap allocations across processors. Remember, I did mention that there's a large object heap per logical processor on server mode, right? So we're actually balancing how much is created on there. And believe it or not, there's even more. And I could probably spend 2 hours talking about GC improvements, but I won't. And so if you are interested in learning more about the improvements I did talk about, or figuring out like what new ones are coming up, there actually are a ton of new ones. Please watch the CLR team blog. I'm not sure if everyone can read that at the bottom right-hand corner of the screen. It's blogs.msdn.com/CLR team/b/CLR team. Just search online for CLR team blog. And we should have a really great article coming up there sometime next week about the other enhancements to the CLR GC in 4.5. So with that, so I spent a little bit of time talking about how these improvements to the GC can reduce pause times for your apps. And reducing pause times helps with runtime performance, right? But there's clearly other performance metrics that you as .NET developers need to be aware of. And who can name some other performance metric that, say, you had to track and optimize for? Yep, startup time. I heard startup time. Anything else? Sorry? Yeah, memory, yeah. So startup time and memory usage are the two big ones, actually. And so this next feature I'm about to talk about is improves both those things. It improves, helps improve startup time and reduces memory usage of your app. And the feature is called Managed Profile Guided Optimization for .NET Apps. I'm sure this is very easy to remember. You guys are used to the 7-word names now in this conference. So for the rest of it, I'll just call this MPGO. And this feature is relevant for the scenarios where you have native images. So how many of you guys, I'm just curious, are using NGen against your app assemblies or have heard of NGen? So a lot of people have heard of NGen but aren't using it, and some people are using it. Okay, awesome. So NGen is basically, if you've been following any of the guidance that's been coming out from the CLR team over the past few years around performance, you may have heard, sounds like a lot of you have heard it, that you should use NGen for your apps to improve performance. And specifically how it improves performance is there's two ways. One is because when you create the native image, when you create the native image for your IL assembly, you're actually compiling the IL code into native code for all the methods. And you're doing that ahead of time such that you avoid the cost of doing that JITting at runtime. And so because of that, your app runs faster, right? Like it launches faster. You're avoiding that cost, essentially. So that's one benefit. The second benefit of NGen is actually is a little bit more nuanced, where what happens is that since it's a native image file and we're loading it page by page from disk into memory, when you load in pages that aren't written to, right? So you load in a page and you don't write to this page, so it's been untouched. It turns out that you can share this page across other processes that might require the same native image file. And so when you do this sharing, you're actually reducing the overall memory usage of your machine across multiple apps. So for libraries in general that you know are going to be used by multiple apps, this sharing has a pretty good benefit. And so in general, so that's how NGen, what the benefits of NGen are. It turns out there are some more optimizations we can make on top of NGen. And this feature helps with that in that space. And so we'll look at what the problems are, right? Like, what are we trying to solve here? So memory usage, clearly big one, things that we should care about. I think the gentleman in the back said that. And startup time, I think someone in the front here said that. So with memory usage, when you're actually pulling in these pages from disk into memory, say you could actually reduce the number of pages that you actually need to pull in, right? So that helps on two fronts. If you could reduce that, that'll actually reduce the memory usage, of course. But the second thing is you save time, because you're not having to page in stuff, right? And in particular, if you're doing a lot of this paging in on your startup path, right? Say you're loading a whole bunch of controls, that first splash screen is coming up. It has a whole bunch of controls that it needs to load from different assemblies. Like, wow, that's a lot of things that you're paging in on the startup path. And if you could eliminate some of this cost in the startup path, your app might actually load faster. Your user can see that first splash screen so much faster. And so if we could reduce this, that would be fantastic. And so the technology that we've come up with on the CLR team, and it turns out this is very similar. Are there any folks who have played with PGO or BBT for C++ and know how profiling works in general? Okay, there's a few folks. So this is basically profiling, and I'm about to just explain what that is. And so to explain that, this is internal stock. Again, you get to see what we're doing here and how we're actually optimizing this. And so the diagram there is supposed to represent the layout of a native image file. So remember, native image files, we actually load them page by page. And so the green dashed lines represent page boundaries. And say now that you have, right in that top page over there, you have this little memory segment that represents a method that your app needs to use when it's executing. And so if it needs that memory segment, it's going to pull in that page, right? And now think that, hey, maybe that last block that's marked hot there in the right at the bottom. Let's say there's another memory segment there that's needed next, right? So now you just pulled in this whole page from the top, and you're also going to, because you need this new method, you're going to pull this other page in, and you didn't even use half the information that was in that first page that you pulled in. So you have this this poor density of usage on your pages, right? And so what if we could actually move that first memory segment, move that second memory segment right next to that first one, because most of the times you know which order your methods are going to execute in, right? There's typical usage cases for how the order in which methods are executed and which methods will ever be executed, right? Like some methods are never touched. Like if you say have exception code paths, then chances are that exception code path is actually not getting touched that often. And so there's clearly an opportunity for optimization here. So if you could actually bunch these guys together, then maybe you could only load a single page. Maybe you don't need to load that other one. And similarly for copy on write, if you could figure out ahead of time, like what are these little CLR data structures that, so it turns out that we do write to some pages. The CLR does write to some pages because of we need to keep some of our internal data structures up to date. And so if you could actually figure out what these data structures are and then bunch the memory segment together for that, then again you can reduce that, right? You can eliminate a page. And so that's the idea behind this. We basically try and co-locate memory segments that are used or are hot together, and we try and co-locate memory segments that are going to be written to together. And so if we do that, we reduce a page there. There's a couple more concepts. I showed a slide there which had the word hot and cold. Basically what it means is if there's a piece of a method or a basic block that is actually going to be executed, that will be executed in your common scenario, we call that hot. If it's not, we call it cold. If there's a CLR data structure that it is written to, then it's called write. It's simple enough from there. So I did say that that these common scenarios, right? And like we should, once the CLR has this data, it can actually influence the layout of your native image in a smart way. Well, how do you get that data? And so this is where you guys come in, and this is where now I shift into the part where you guys will actually. So the next couple of slides will look at how you use MPGO. Okay, so the first few slides were just the breakdown of how it works internally. But this is now how you actually use it. And the way you use it, there's actually 3 phases. The first phase is the build phase, where you're actually creating your assembly, and at this point you want to identify the common scenario under which your app assemblies will execute. So say you have a very simple timer app, all it does is it puts up a splash screen and just counts down, right? Then you know what, that's your common scenario. If the app can do nothing else, then that's it, right? And you need to identify what that is. And then you have to trigger the CLR to generate profile data, so basically collect that list of what methods are being executed or not. And then the CLR also needs to be triggered to embed that data into the IL. And then the setup phase is super important because this is where you actually need to go and generate a native image. And once the process of generating the native image will do that fancy layout for you. So you have to be using Engine, right? So if you're in the Engine world, this feature is for you. And lastly, it's the run phase where you can actually realize the benefits of using MPGO. So at this point, I'm actually going to show you a short video that walks through this workflow. Before I put the video up on the screen, I'll say that the video is using VS 2010, Visual Studio 2010, and it's running mpgo.exe from a VS 2010 command prompt. Don't get too excited. We don't have MPGO available in VS 2010. It's just an early prototype that my team had put together, but I thought I'd show it anyway because it's fairly instructive on how you can use this tool. Okay. Hold on. So my machine went to sleep here. All right, so let's start taking a look at this. So you see here that there's 3 files. There's install.bat, there's large application.exe. Notice that it's 80 megabytes. And install.bat and uninstall.bat will simply engine that large app.exe. It's fairly straightforward here. So you see what it has over there. and it uninstalls it. And then for good measure, of course, we're actually going to run largeapp.exe after enginning it. And typically you want to engine because you want to get the benefits of warm startup time. So we run the large app, and in this case, we've actually instrumented this app to dump out what its cold startup time and working set is. So it's 5 seconds, 50 megabytes. So now the next step is actually running mpgo, and I'm actually going to show you how simple it is to run. So you run mpgo.exe, you provide a scenario that you want it to execute, and the scenario is going to be largeapp.exe. Clearly, this is a very simple app. And then you provided a list of assemblies for which you want to gather profile data, right? So you can actually at this point specify the exact assemblies for which you want profile data. Maybe you don't want to get profile data for all your assemblies with that particular scenario, right? You can actually choose what scenario you want to use for each assembly. And then you dump the profiled library into a folder. And you also, you actually get to specify a timeout value after which we should stop profiling. Because typically you want to profile your startup path. And so if you know how long your startup path is, then you only use it for that much. And then now that we have that, we go ahead and run that exe again, just for good measure, just to make sure it works. And now the most important phase comes after this, where we actually, the thing I want to point out here is that you'll notice that largeapp.exe is actually 81 megabytes now. The reason for that is that profile data got embedded into your IL. So we generate that, and the CLR will embed that data in there. And so you can see the videos running a bit ahead of me, but we're actually running nggen install to create that optimized layout. Remember, nothing happens without running nggen. And then when we run the app, you should see cold startup time and working set improve. So it turns out that the tool actually is not part of your Windows 8 developer preview machines that you have, but it will be made available on our blog. So again, that blog link is fairly important to remember. This is just the usage of mpgo. I showed that in the video. It takes in a scenario, and you can specify the list of assemblies you want to profile for. So with that, I guess I went a little out of order there. But with that, I think that continuing on the theme of performance, you should have seen we're doing a ton of performance improvements. And Mark's actually going to take over from me at this point and talk about a few more performance improvements we've done in 4.5, as well as the last diagnostics improvement. So with that, thank you.
Cool. So earlier when we were talking about nggen, Pratiti asked how many of you guys have written an nggen install app, and so a few hands went up. And then she asked how many people knew about nggen. A lot more hands went up. Can anybody kind of give me an idea of maybe why that is? Click once. Okay. So there's some cases where nggen can't be used, and we'll talk about those later. What else? What might be another reason why you guys aren't using nggen? Say that again? Silverlight server apps. Okay. For the people who have made installers that take advantage of nggen, that install their apps with nggen, how many of you guys thought that was like a really easy thing to do? Like it was awesome experience? Yeah, no hands went up. So one of the things that we've been doing in .NET 4.5 is creating automatic nggen, and I'll share some of the challenges that we've had in previous what I'll call classic nggen, just for the sake of distinguishing it from automatic nggen. So we have kind of three categories of challenges that we have. One is the .NET Framework install size. I was sitting next to a gentleman in Joshua Goodman's talk the other day, and he said something about the .NET Framework install size, and the guy sitting next to me yells out, "It's huge!" And I thought that was pretty funny. But we've been working really, really hard in .NET 4.5 to reduce the impact of the size of the .NET Framework. Another challenge in this space is difficult setup authoring. As I said before, nobody raised their hand when I asked how easy that was. And then the third thing is managed Metro-style app performance. We really wanted to make sure that managed Metro-style apps that you've written in C# or VB really feel really feel fast and good, and we see Engine as a potential solution to that problem. I want to take a step back and talk about framework install size for a second. Most of you are aware that in all the way up to .NET 4.0, we created native images for every assembly that we ship as part of the framework. Every assembly that's in the box gets its partner native image when we install the framework. So you can kind of think of that as doubling the size. And sometimes native images are bigger, and so that's a little bit more, but just think of that as doubling the size. In addition, you may have more than one framework on a machine. So the Windows 8 boxes you have, if you run into the 3.5 install on demand feature that Josh talked about in his talk, then you also get 3.5 on your machine. And so historically, we've done native images for every assembly in the framework. And so now you've got multiple frameworks that are both doubled, and you've got this compounding thing. And then if you're on a 64-bit box, you know that we install both a 64-bit version and a 32-bit version of the framework. And so that compounds it again, and things just keep getting bigger and bigger and bigger. And we realize that this is not scalable. This is not where we want to be. And so to solve that problem, well, that's easy. You just don't do that anymore. You don't create native images for the whole framework. So we did a lot of research, and we looked at what assemblies are being used by most apps. And it turns out there's this fairly core set of assemblies that are used by most applications. And we call that set the frequent set. So that's the set that we engine out of the box. So when you install the .NET framework on Windows 8 4.5 starts with this core set that we call the frequent set engine. And we do the same thing for 3.5. So this core set. So great, we solved that problem. Things are smaller now, but the problem is we've left some performance on the table. The blue there represents, we've made this gap between where we used to be and where we are today, and we still need some solution for that. So before I talk about the solution, I also want to talk about the classic engine model and talk about the difficulties there. So before, we have kind of these three separate steps. You've got to install your app, and at the install time, that's when you create your native images. You call engine install. You've got to figure out what's the right set of command line arguments to pass to that thing. You've got to figure out how do I write the right custom action so that your MSI does that correctly. There's a lot of pain there. And then when your app is uninstalled, you've got to do the same thing. You've got to uninstall the apps. Or when you upgrade your app, you've got to figure out how do I get my assemblies updated and then get my engine images updated to match those things. When really where you want to be focusing your time is on the center box, writing great apps. Focusing on code that you enjoy writing, that you really want to spend time on. And so we really wanted to take a step in the direction of letting you guys focus on there and not having to worry so much about install and uninstall. And so to do that, we've implemented this thing called Auto Engine, and I'll talk about the Auto Engine model. Notice install and uninstall is not part of this life cycle at all, and we've taken that out of the picture. Now we still allow you to write apps that make use of installers and make use of engine install and engine uninstall and engine update and those kinds of things. So those things are still available. Your apps, your existing installers will continue to run the way they do. But for those apps that don't take advantage of engine because it's too complex, it's too hard to worry about, we're helping to bridge that gap for you and do some of this automatically. So the green box there is you can think about that as the same box that I had in the middle on the other slide. This is where you want to spend your time, writing a great app and a great app that runs. And you can see I'm talking about myapp.exe, which is a really sweet app that I made. And you can see that I've got several boxes on top of each other, and that's kind of the sweet PowerPoint way of indicating there's more than one thing kind of going on in your machine. You don't just use one app on your machines. You're running several different apps. And so now with .NET 4.5, when managed apps run, they create what we call assembly image usage logs. These things go out into a directory. If you guys are looking for them, they're buried down underneath app data. So if you look at your local app data, you can dig around under Microsoft .NET Framework and find these things. Since it's an internal stock, I can tell you that, but don't go in there and try to do something with them. So what the usage logs contain is information about what are the images that were used when the application ran. You know, what managed assemblies did you pick up? If you were using any native images, what native images got picked up, and we store that stuff for later. And what's at the bottom here is the auto engine maintenance task. This is what's new. This is kind of replacing the old engine service that we had. So on Windows 8, we don't have the engine service anymore. We have this maintenance task. And it takes advantage of a Windows 8 feature called maintenance time. And if you've been to some of the Windows talks, they may have talked about that. This is a time that Windows identifies as saying, hey, the user's not, they're not browsing the web, they're not running any apps, they're not watching a video. This would be a great time to do some stuff, do some maintenance stuff to make the system run faster. You can think of things like defrag as kind of fitting that category. So we plug into that time. And during that time, when we run, we pull in those assembly image usage logs, all the ones that we can find on the machine. We pull those in, and we do some processing, and we figure out what's the set of native images that we might want to create. So for example, here we've got myapp.exe. It's going to show up somewhere in the assembly image usage logs. And AutoEngine is going to say, hey, this person has installed a new app. They're using a new app. It's running this managed assembly. It could really benefit from having a native image. So it creates a native image for that without the developer having to worry about that at all, not having to write up any plumbing, any complicated installer. It just works. One of the other things that the AutoEngine usage task, AutoEngine task does is it looks at the native images that are on the system and says, well, how many of these things are actually being used? How many of them show up in the usage logs? So it looks through there, and any native image that is not being used, maybe it hasn't been used in like 60 days or something. Somebody had downloaded an app and used it for a little while and decided it wasn't for them. It's not being used anymore. They haven't uninstalled it from their system, but it's still there. We created a native image for it, but we don't need it anymore. And so it can actually figure out which native images aren't needed, and it can remove them. Now, before you get worried about the great apps that you've already written that use native images, AutoEngine's not going to remove any of those. The images that you guys install with Engine Install, they have what we call roots. They're rooted, and so rooted images that are installed with Engine Install are not removed by AutoEngine. The images created by AutoEngine, however, don't have roots. They're what we call rootless images, and so their rootedness is based on the assembly image usage data. So that's the thing that's keeping those things around. So when native images are not being used any longer, then they're eligible to get removed. So I want to talk a little bit about how AutoEngine is configured today on the Windows Developer Preview. It's kind of in this really aggressive mode to let you guys experience it and to give us feedback. And we'd really like you guys to see how it interacts with the apps that you guys have already and the apps that you guys are writing, and really give us feedback, because we really want to hear that so that we can tune this thing to work the way that would really be best. So to start out, Automatic Engine is a Windows 8 only feature. I talked about how it makes use of the maintenance time there in Windows 8, and so it can only work on Windows 8. On down-level OSs like Windows 7, Engine continues to work with the Engine service. Nothing changes there. Good question. My next point is that this maintenance time really only makes sense on Windows 8 client. So in Windows 8 Server, you don't have this notion of a server sitting around doing nothing. The whole idea is that they're doing stuff all the time. And so AutoEngine is not enabled on server. And they still have the engine task that takes care of the regular engine stuff, but the automatic lifecycle there is not enabled for server. So as I mentioned before, we're doing the frequent set, the smaller set of images out of the box for the 3.5 framework as well. But on 3.5, only the .NET 3.5 assemblies are eligible for AutoEngine. We're really just using AutoEngine in that case to close that gap between the frequent set and the assemblies that are used. So on Windows 8, if you enable 3.5 for only one specific application, we're only going to create native images for the parts of the framework that are used by that application. So we get the right trade-off between disk space and the performance for those applications. For .NET 4.5, there's a couple of other interesting caveats here. For .NET 4.5, we felt like it was really important to not enable AutoEngine for for assemblies that were never targeting .NET 4.5. So if you have an app today that's compiled targeting .NET 4.0, those assemblies won't be auto-engine. So if you want to take advantage of auto-engine, you want to play with it, you need to recompile your apps targeting .NET 4.5. So there's two categories there. The desktop apps, which are the apps that you're used to writing. For those, only assemblies that are located in the global assembly cache are eligible for auto-engine. Prachiti talked about engine being really useful in those sharing situations where you can reduce the working set because things are being shared. And so in Metro-style apps, today in the Windows Developer Preview, all assemblies are eligible there. So when you write your Metro-style app today, AutoEngine is going to kick in very aggressively, and we really want your feedback on how you guys feel like that's affecting your apps. We want to get that feedback. So play with the developer preview, write Metro-style apps, run them, see what's going on. You can dig into the native images that are getting created and take a look at those. So automatic engine for Windows 8. So we talked about some other stuff. Did you have a question? Okay, sweet. We talked about engine, and some people were mentioning other scenarios why they're not using engine, and they talked about things like server platforms, Silverlight, and things like that. There's some places where engine simply can't reach, so we've got this gap. And so for those scenarios, we have another feature called multi-core background JIT. And for those scenarios where engine can't reach, startup still matters. You still want your app to start up fast. JITting takes time. That's the thing that engine really helps with on the startup path is removing the JITting that needs to happen. And on most machines these days, they've got multiple cores that are just sitting around doing nothing while your app is starting up. Most app startup paths are single-threaded, and so there's a lot of resources that are just going unused. And so multi-core background JIT attempts to utilize some of those unutilized resources by giving them something to do. And in this case, what happens is the first time that you launch your application, it starts to create this profile of executed methods. So the CLR starts keeping track of all the methods that it's hitting as it goes along its startup path. And it builds up this list in the order that it hit them, and it stores that off. So that on subsequent launches, we can pick up that profile. We can say, hey, we've got some work that we can do. We can spin up a background thread and say, hey, can you start speculatively JITting these methods? Try to say that 5 times fast. It's very difficult. Start speculatively JITting those methods. And in this case, a lot of times, for most of the things that we see about a 10% performance improvement from allowing this to happen. So to enable this, we've got a couple of new APIs. This is one of those things where it does require a little bit of work on the code side to make this to kick this in. So we've got these two methods here on this profile optimization class, static methods. One of them is set profile root. This just says, hey, this is kind of the directory where I want you to store profile information. And the second one is really the interesting one. So the first time that you call start profile, and you give it this file, what amounts to a file name, the JIT is going to say, okay, this is my cue to start gathering this profile data, and I'm going to store it in this location. The second time that you call it, it's going to read in that profile and say, here's the work to do, spin up the background thread, and get it started. So this second method is kind of a dual-purpose API. It serves as both the trigger to start and the trigger to start profiling and the trigger to start executing the background JIT. Now you may be wondering when should you call this thing? Obviously you want to call this as early as possible on your startup path. But it's important to note that we've been working with our partners, and in ASP.NET 4.5 as well as Silverlight 5, two of the scenarios that people talked about not being able to use engine, this feature is automatically enabled. And on ASP.NET 4.5, this, along with another feature where we allowed the OS to turn on the prefetcher, that will actually, the numbers that we saw there are actually saving about 35% of startup time, which is really important for the hosting scenarios. So hopefully you guys are excited about that. You guys who were talking about these particular scenarios, Silverlight and ASP.NET stuff, should be very happy about that. I'm sorry? So Azure's not running on .NET 4.5, so no. So we talked a lot about performance. We talked a lot about engine and things, startup performance and working set. I want to switch gears for the last feature. We think this is a really interesting feature because it not only shows that we're doing things, these kind of on-demand things, but we're also looking ahead and doing other features that are longer lead, kind of enabling features. This one is called Regit, but Regit really doesn't tell you a whole lot about how you use this thing. And so I've got this sub-bullet here, the no restart production monitoring. So how many of you guys are doing any kind of production monitoring? Okay. Do we have anybody here who has written a CLR profiler before and doing like instrumentation with profilers? Great. A couple of you guys. So good. So you guys doing production monitoring know that production monitoring is becoming a really popular way of making sure that large enterprise-type systems are running healthily, that things are going well. You may have agreements with service-level agreements with people that say, oh, I need this amount of uptime, this amount of throughput, things like that. So you use production monitoring to make sure those types of things are running well. You can imagine like these big dashboards with green lights and stuff, and when one of them turns red, you know you've got a problem. Most of these systems work with profiling. They profile using our CLR profiling APIs and inject instrumentation into these systems so that they can gather that diagnostics data. Well, the problem with this is that this instrumentation adds overhead, so you can't just go blast through your entire app and add instrumentation out the wazoo, as it were. You really want to find that base level of instrumentation that gives you enough information to know that nothing's going wrong, but not so much that it's overbearing. Well, the problem is that that level of instrumentation is not always enough to diagnose problems, and so you end up having to go back and do deeper level instrumentation, and today that requires an application restart. So I've called out another talk here. It talks about using IntelliTrace in production with Visual Studio 11. They're not using this feature, but if you guys are interested in production monitoring and things like that, that would be another good talk to see how IntelliTrace is doing that today. So I wanted to give you an idea of something that an instrumenting profiler might do. The green here is IL code. This is an internals talk, so we get to look at cool things like IL. The green code here is IL that was created as a result of compiling C# code. It's the regular code that would get emitted by the compiler for that. The red code would be maybe the kind of thing that a instrumenting profiler might inject. In this case, we're just calling this increment telemetry method, which is probably just doing something like incrementing a variable and then servicing that to some telemetry system, so you know that you're getting, in this case, it's a transactions in progress, so you know that the number of transactions in progress is not going above some threshold that you don't want it to. Just to give you an idea of what, for those of you who haven't done anything with profiling and injection. So I'll run you quickly through a production monitoring scenario the way it works today with .NET 4. So you have a process start. You've got to start your process in order to do anything. You've got some base level of instrumentation that happens. And after a while, maybe there's a problem that's detected. One of those things goes up over a threshold. You say, oh, no, something's going on. I need to figure out what it is. Well, today, in order to instrument more fully, you've got to restart your process. And the reason this is that the way that you inject code with the profiler is by getting in between the runtime and the JIT. As a profiler, you get to know when a method is going to be JITted for the first time. You get to inject yourself into that process, rewrite the method however you want, and then hand it back off to the JIT. And in .NET 4, you only get one chance to do this per method. And so if you want to do something different, you've got to restart the process. So we restart the process, bigger amount of instrumentation. Now we have enough information to diagnose what the problem is. Oh, figured out my database transactions are going more slowly. I need to call up my DBA, get him to reindex a table or something like that. Now I can see, yay, it's running the way it should. But now I need to go back to that baseline level of instrumentation. And to do that, I've got to restart the process again. So you can imagine a process restart in a big enterprise system could be a very disruptive kind of thing. What if your problem only reproduces itself after 8 hours or so? You just signed yourself up to sit there and watch the system for 8 hours on a Friday afternoon when you'd rather be doing something else. So what we'd like to do is take the process restarts out of there. And with regit, that's exactly what we let you do. So with regit, you no longer only get one chance to get in between the runtime and the JIT. With regit, you get to say, hey, I need to change something. The next time you're going to run this method, let me know, and I want to do something. So in order to do this, we've added some interfaces to our profiling interfaces, and so the things in red are the things that are different. This is not the full set of things that you need to do this. Writing a profiler is a complicated thing, as I'm sure some of you guys who raised your hand would tell you. These are C++ interfaces, which is what you have to write a profiler in. The first one is not a new method, but we've added an extra flag that we need to tell the runtime, hey, we're going to use regit, so can you keep track of the things that you need to keep track of in order to enable regit? And the second one is kind of the meat here. This is when you get to say, hey, you know what, there's a whole set of methods that I would like an opportunity to rewrite. I would like to regit those things. So let me know the next time you're going to run that method, and I want to jump in there and be a part of that. And so you're basically giving it a list of methods in that case. And so the next time that the JIT hits one of those methods, it's going to call you back on this get regit parameters and hand you an iCore profiler function control. And hanging off of that interface is this set IL function body, an existing function, but that's the one where you get to say, no, don't JIT the IL that you think you have right now. Here's the IL that I want you to JIT instead. So if any of you guys who are writing profiling, instrumentation profilers, our diagnostics team would love to have a chat with you, and if you guys are interested in this feature, let me know. So we talked about a lot of features today. We talked about background GC available for server mode, which allows the short allocations to continue while the long collections are happening. We talked about MPGO, now available for .NET to help you with your memory, with your working set, as well as startup time. Automatic Engine is automatic. We've reduced the install size. Something I didn't mention earlier is that on Windows 8, .NET 4.5 is 40% smaller than .NET 4.0 was.
Yeah.
And in the extreme case, where I talked about you've got multiple frameworks, 3.5 and 4.0 on the box, you've got 32-bit and 64-bit. In that extreme case, we save up to half a gigabyte of space. So really reduce the footprint of the .NET framework. ASP.NET and Silverlight 5, both using multi-core background JIT, and you can use that in your own scenarios. I talked to a gentleman last night, and we chatted about how he could use this in his scenarios.
Yeah, I think Silverlight 5 RC, I think those bits were released just recently. That is using this already. So.
Yeah. Production monitoring no longer requires app restarts. So this is not the full list of things that we've been working on. We thought we'd share with you kind of a potpourri of things. Hopefully you're interested in those things. But as Prachiti said, keep an eye on the CLR team blog. You'll see more and more articles coming out now that we've announced .NET 4.5 and all the features. Again, these are the sessions that we called out during the talk that you guys might want to follow up with. In addition, if you guys didn't get a chance to see Joshua Goodman's talk, I think that one's up here.
Yeah, that's the first one.
So the first one is
What's
Joshua Goodman. The second one was Christoph's talk that he did just before this one, or two.
It was at 10:30
sometime
today.
this morning.
Yeah.
It was a really great talk. Cleared up a lot of confusing things. So thank you guys very much. We don't have time for questions now, but Prachiti and I will both be down in the expo hall at the .NET Framework and Visual Studio booth.
Yep.
So thank you very much.